I'm going to tell you about some work that I did a little while ago, formalizing things called Lie algebras. Now, of course, by formalizing, I mean formalizing in a proof assistant, in this case, Lean. But I didn't just use Lean, I was working with Lean's mathematical library that we call Mathlib. And the key feature of Mathlib is that it has a focus or an emphasis on mathematical unity. So in particular, that means that if we build any theory of mathematics in one corner of Mathlib, and then maybe at a later point in time, somebody else is using some other theory, we want both theories to be completely compatible. So for Lie algebras, for example, when the time comes that we're talking about holonomic groups of Riemannian manifolds, well, these holonomic groups are Lie groups, thus have Lie algebras. We want the Lie algebra theory that I'm building to be available to that person. So what I really wanted to do was to build a usable theory of Lie algebras within Mathlib, not just formalize them for their own sake. And I didn't know at the time, but this seems to be the first time that somebody's formalized Lie algebras on a computer. Now, just before we jump into the axioms, in case you've never seen Lie algebras before, I should emphasize that Lie algebras are everywhere. They're not some esoteric thing. Even if we take this beautiful old problem of planetary motion, they show up crucially there. So there's a fun little calculation we can do. So here we have a picture. This is supposed to be a planet going around the sun, the point O, which I probably should have called the point S. That's supposed to be the sun. And you have the planet orbiting it in an ellipse shape that Newton and his buddies worked out for us. And one of the first things you notice is that the motion is planar. It's fairly intuitively obvious because the gravitational potential is spherically symmetric. There's no torsion or twisting in it. But the question arises, how do you actually prove this? And the trick that we teach to kids is you say, well, let Q be the position vector and let P be the momentum vector of this planet that's doing the orbit. And consider this vector J, which is what we call the cross product. So in 3 dimensions, we have this very nice cross product where you have 2 vectors and you can form a third vector. So you take the 2 vectors and then the third vector is perpendicular to both of them and has the property that it grows to a maximum length as they become right angled and it shrinks to 0 as they become parallel. So this beautiful product that exists in 3 dimensions allows us to form this vector J. J is perpendicular to the position and the momentum. So if J were constant, then these 2 vectors would have to stay in a plane, namely the plane of all vectors perpendicular to J. So that's a means of proving that the motion is planar. Show J is constant, and how do you show something is constant? When you calculate its derivative, you show that 0. So that's what we do. And here, using the physicists love this notation, you denote the time derivative just with a dot. So there's a little calculation that you can do. And you calculate the derivative. This is the derivative of J that we're calculating. And it comes out, and ultimately the answer is 0. So this is the proof that motion is planar. But what do we take away from this? Well, it is eventually 0 because it's a difference of 2 zeros. So the first 0 is, well, q dot, that's the speed, that's the derivative of position. And p is the momentum. So the speed and the momentum, they're parallel. And the cross product of parallel vectors is 0. So that's that 0. And the second, well, we have the derivative of momentum. That's the gradient of the potential. This is F equals ma. And because V is spherically symmetric, the gradient is parallel to the position. And so that's 0 as well. So the 2 facts that we needed were that a vector crosses itself is 0 and the potential is spherically symmetric. So this is a good example of the shape of Lie theory. You have some symmetry, in this case it's a group of rotations coming from the fact that the gravitational potential is spherically symmetric. And you have a special product, which in this case is the Cartesian product. We've already seen that it satisfies this property that V cross V is 0. And it satisfies one additional property, which is here. It's not associative, but in place of associativity, it satisfies this little identity known as a Jacobi identity. So that's our first example of a Lie algebra. So just keep in mind, they show up everywhere. Now, let's look at the axioms. So you have a module over a commutative ring. If you prefer, think vector space over a field. You have a bilinear product, usually denoted with square brackets like this. And it satisfies the 2 properties that we've just seen. The vector appearance itself is 0, and this is the Jacobi identity. And that's it, that's a Lie algebra. So what are the examples? Well, actually the calculation we just did was showing that angular momentum is conserved for a spherically symmetric system. Linear momentum, similarly, has its conservation stemming from translational symmetry. So linear and angular momentum conservation are best understood via symmetries and via Lie algebras. As you study classical mechanics more deeply, you come to understand that actually the set of observables themselves, that should be a primary object of concern. And you recognize that it carries a product, namely this Poisson bracket, which is actually a Lie algebra product. And it's very important for quantization. So that's another place where Lie algebras crucially show up in physics. Another example is elementary particles like quarks or electrons or neutrinos. These all have these fascinating internal symmetry groups, which are Lie groups, and thus they have Lie algebras. And understanding these elementary particles requires understanding the Lie algebras. So they're showing up in really fundamental places throughout physics. And then, of course, in pure mathematics, they're everywhere. So really, the paradigm is that whenever you have a continuous set of symmetries, if these form a group, then that group has a Lie algebra. And you understand the Lie algebra, you use that to understand the group, and use that to understand symmetries. So they really are a tool for studying symmetry. And then, in a sense, you can regard everything else as a consequence of that. Like, for example, multidimensional calculus, the vector fields on a smooth manifold carry a Lie bracket. This is really what you're saying is to take a derivative in more than one dimension, you need to pick a direction. If you pick two different directions, you can go in this direction and then that direction, or you can differentiate in that direction and then this direction. And those two operations might be different. And the reason for that is the existence of a Lie bracket. Or curvature. So again, in 2 dimensions, curvature is just a number. The plane is flat and the sphere is positively curved and the saddle is negatively curved. But as you go up in dimension or you consider other types of geometry, curvature is no longer just a single number. It's a whole collection of numbers. And the way to understand that collection of numbers is to spot that they're parameterized in part by Lie algebra. So to understand curvature, you need to understand Lie algebras. In symplectic geometry, the moment map and symplectic quotients, which generalize the momentum and angular momentum examples we saw before, these are key constructions. And just so that not all my examples need to come from geometry, in number theory, the Langlands program, page 1 of step 1 is defining an automorphic form. And for that, you need to start with the center of the universal enveloping algebra of the Lie algebra of a reductive linear algebraic group. So the algebras are required, straight away, even just trying to get that theory defined. So they show up everywhere. So why should the formal mathematician care? Well, when I'm behaving as an informal mathematician, I essentially care about, or rather as a formal mathematician, I care about a superset of everything that I care about as an informal mathematician. Or another way of saying that is that it's necessary to formalize Lie algebras if you ever want to formalize many, many fields of mathematics. Just a job that needs to be done. Very nice, fun job in my experience. Also, looking at Mathlib maybe a year or so ago, formalizing Lie algebras was an opportunity to explore some non-unital and non-associative algebra. So the library at the time had a pretty good theory of unital associative algebras, but nobody had yet needed to push it much in the direction of non-unital and non-associative algebra. So the algebras were an opportunity to explore that ground. And one of the things I liked about the project was there was an obvious early milestone. So there's a beautiful Cartan's classification of Lie algebras is a beautiful result. But it's a moderate amount of work even just to get to the point where you can state the result. So I thought that would be a good milestone. And it's also a really useful result. It gets used all the time in mathematics. So it's just something that has to be added to the library in due course. So I set that as a target. And I got there. We can look at what it looks like in Lean today. So in the simplest possible case, you give yourself the best coefficients you could hope for. So this is a field that's algebraically closed of characteristic 0. And you take a finite dimensional Lie algebra over that field. And then the theorem says that that's what's called simple. So this Lie algebra is simple if and only if it belongs to this list. So we should look at this list a little bit. So there's down here, there's 3 infinite families of Lie algebras on the list. So this SO, this is Lie algebras that exist essentially because of rotational symmetry. And this SL, well, these are Lie algebras that exist because of volume preserving symmetries. And the SPs similarly have an intuitive geometry. It's only slightly more complicated to describe. So there's these 3 infinite families of quite intuitive symmetries that give Lie algebras that are on the list. But there's this wonderful dividend from Cartan's classification, which is there's just 5 more cases. There's an infinite family and there's these 5 more. And these are the so-called exceptional Lie algebras. So if you want to be able to state the classification theorem, okay, you have to be able to say what it means for a Lie algebra to be simple. And you have to be able to define these SL, SP, and SO. But you're also going to have to be able to define these exceptional Lie algebras. And so the question is how to do that. It's not totally trivial. So I thought a little bit about that, and I decided to use a construction essentially due to Serre, where you start with a matrix. In this case, I've given the matrix of the largest of the exceptional Lie algebras, E8. And this is literal copy and paste from the Mathlib source. So you start with a matrix, and you build a Lie algebra out of it using this function, 2 Lie algebra. So, okay, so that's the definition of E8, but there's quite a lot going on under the hood. So the real question is, how is this function 2 Lie algebra implemented? Well, that's a two-step process, really. You have your matrix A. We saw an example just a moment ago. You construct what's called the free Lie algebra. So we're going to do the Lie algebra equivalent of constructing a group with generated in relations. So we start by constructing this free Lie algebra, and this is this giant infinite dimensional Lie algebra. And then we take a quotient by a bunch of relations that Chevalier and Serre worked out in the 50s or 60s. And for appropriate matrices, that quotient will give us a finite-dimensional simple Lie algebra. And so then we can feed in the relevant matrices for the 5 exceptional algebras, and that'll give us usable definitions. So that really, the quotient, I mean, of course, you have to be able to define the ideal by relations and prove that the quotient of a Lie algebra by a Lie ideal is another Lie algebra and so on, but that's all quite easy. But constructing the free Lie algebra, that was a little bit of work, so it's worth saying a few words about that. Okay, so how do you construct a free Lie algebra? Well, there's 2 pieces of input. There's a type, no structure at all, just a type x, and then you have a commutative ring, that's your coefficients. And you want to construct the free Lie algebra, so free Lie algebra on x with coefficients in R. And we do this by really first constructing this object, lib_rx. That's where most of the effort goes, is constructing lib_rx. So lib_rx is the free algebra, so it's an even bigger object than the free Lie algebra. And how do we construct that? Well, all of these free objects, you look at their universal property. So the universal property is, let's suppose that we had a definition of lib_rx. Well, the universal property it's supposed to satisfy is that morphisms in the category of algebras, this is non-unital, non-associative algebras, from it into any other algebra, these are supposed to be in bijection with morphism in the category S for sets. And this is A for algebras, so this tells us which category we're in. It's supposed to be it's a functor adjointness, so it's supposed to be a bijection of morphisms like this. So I wouldn't worry too much about the details, just that this is the property that we need to satisfy. So say, okay, I need some object lib_rx that satisfies that. How can I build that? Well, it's not too hard. It's a 2-step process. So first of all, just given a type, no coefficients, you can build something called the free magma. And it has its universal property. Again, we're in the category here. This is sets again, and this time this is an in-between category of magmas. Again, don't worry too much about the details, but this is universal property. Mathlib already had the free magma, so I could just use that. And then there's a construction of how to build an algebra from a magma. We're going to plug in the free magma in a moment, but just before we do that, for any magma, you can build a free magma Rm, and it has this universal property. So if you collect together the universal properties that we've got, these are the 2 that we just saw. We compose them like this, and we see that the magma algebra of the free magma is exactly the right universal property that we need for lib_rx. So we take that as a definition, and we construct a free Lie algebra as a quotient. And what does that quotient look like? Whoops. That's what it looks like in Lie. So, okay, there was a bit of work, mostly in universal algebra. We constructed the free Lie algebra. What were the lessons? Well, the route that we took was a lot more work than sort of a one-off ad hoc approach we could have taken. It was, in principle, it was better because it was less single-use code, it was more maintainable, it's closer to what the informal mathematician would do. But the dividend as well was that it forced us to generalize Mathlib's algebra hierarchy to enable us to talk about non-unital, non-associative algebras. And now, 6 or 7 or however many months later it is, independent work is arriving with people working with Jordan algebras as they're about to be defined. These are non-associative. They're going to use the additions we make to the algebra hierarchy. And we have C-star algebras, and these are in due course going to be generalized to the important case of non-unital C-star algebras. And again, this will reuse stuff that we added when we were building the exceptional Lie algebras. So it's a nice endorsement of Mathlib's paradigm of always pushing to take the unified approach and so on. Yeah, we have the classification theorem. You can say, how much Lie theory do you have? Well, we have Lie algebras, Lie modules, submodules, ideals, morphisms, extension and restriction of scalars, tensor products, direct sums. We have nilpotent, solvable, simple, semi-simple, all of those concepts. With the radical, we know it's solvable. The center, cartan subalgebras, weight spaces, root spaces, universal enveloping algebra, classical exception algebras. So you can say where to from now. We've gone a fair bit beyond the classification statement. I think we could go for the result, the proof. I think it will be a lot of fun, a lot of work, very useful, and entirely achievable.
Thank you very much. Let's thank Oliver. Interesting talk. And we're ready to take questions. Are there any local questions?
Questions from Philly.
Okay. We have an online question from Mevan, if we can post it.
Right. Yeah. So how did I deal with this? I mean, I just make a definition and.
Sorry for the bureaucracy. Let me just read it first aloud.
Right.
So you're talking about the free Lie algebra, but this uniqueness is only up to isomorphism, I guess. How did you deal with this in the formalization? All right. Please.
Yeah. So I mean, if you're mathematically, because this object only exists up to isomorphism, any mathematical statement about it that you want to make, only ever needs it up to isomorphism. So you build it with a particular definition, which I even sketched. It's a quotient of some other algebra, and then you prove that this particular construction, which you don't care about, all you care about is that it has this universal property. So you prove the universal property, and then that's all you ever actually use. So any mathematically meaningful statement that you want to make only ever needs the universal property. But you're absolutely right though. That question is sitting there in the background, but it's just kind of standard. I mean that phenomenon exists in informal mathematics to the same extent.
All right. Any other local questions?
No.
We have a question from Ralph. Can we please post it?
Oh, okay. Yeah. All right.
Could you please quantify better how much is already formalized in terms of hours of a graduate course on this topic?
That's a really good question. I would say if you're I'd say like 5 hours of a graduate course, something like this. Maybe it kind of depends. But yeah, not a huge amount. At the graduate level, not a huge amount.
All right.
I'm picking that number totally off the top of my head, but I'm just thinking, and where would you start as a graduate course anyway? Do you assume these people know what the algebras are and you're picking up and you're trying to, because we actually teach the classification theorem in advanced undergraduate courses, but then there are also people who, so allowing for the fact that there's a bit of freedom to interpret the question. Yeah, I mean, I'd say maybe 5 hours is a bit conservative. 5 to 10 hours, I'd say, something like that.
All right. Another question from Loic. If we can post it. The Cartan classification theorem seems to be talking about finite dimension things only. Do you know if it can be made constructive?
Right. So I have no idea in the sense that, it's such a tower of mathematics underneath it that, I couldn't possibly guess, but I doubt it. I'm a completely classical mathematician, so I never even consider not using the law of excluded middle. It's true that it's talking about finite dimensional things, but it's talking about finite dimensional things over, in the simplest case, the complex numbers. I'm not even especially well versed in how to be constructive, but I don't think it's trivial to be constructive in that setting. I suppose you just need characteristics of algebraically closed fields. Yeah, I should say, I'm not especially well qualified to answer that, even though I know the mathematics, because I'm really just a completely classical mathematician. But my guess is, or rather, more than a guess, I'd be surprised if you could do this constructively. I noticed that it's interesting, that people are very interested in being constructive. The culture that we come up with mathematicians is so strongly in favor of just using the excluded middle. I wonder why we would want this to be constructive. I'd love if somebody could comment on why you'd want that.
Okay. Yeah. So this is a really interesting and long discussion.
Yeah.
Andrew Appel also suggests that that's a great lead into the next talk.
Yeah, exactly.
Yeah.
So all right. So let's thank Oliver again.